The Astra mk-3, also known as Gandiva, represents a pinnacle in India's pursuit of advanced air-to-air missile technology. Developed by Defense Research and Development Organization, this beyond visual range missile is designed to equip Indian Air Force with a weapon capable of engaging target at unprecedented distances up to 340 kilometers while maintaining supersonic speeds. Its journey from concept to reality is a story of ambition, innovation, and perseverance, marked by significant technological challenges and evolving design philosophy that reflects India's growing self-reliance in defense manufacturing. The Astra missile family began with Mk-1 variant, first unveiled at Aero India 1998 and officially sanctioned in 2004 with a budget of 955 crore, equivalent to approximately 34 billion rupees or $390 million, led by Defense Research and Development Laboratory (DRDL) with support from Hindustan Aeronautics Limited and Electronics Corporation of India (ECIL). The initial Astra Mk-1 aimed to provide a BVR capability with a modest range of 25 to 40 kilometers. However, control issues and performance deficiency at high altitude prompted a redesign by 2006, resulting in a lighter, more agile with a range of 110 kilometers by time it entered limited production in 2017. The success of the Mk-1 laid groundwork for more ambitious variants, the Astra Mk-2, with a range of 160 kilometers, incorporated upgrades like dual-pulse rocket motor and indigenous ESA electronically scanned array radar seeker, pushing the boundaries of range and precision. Yet it was Astra Mk-3 that truly embodied a leapfrog driven by integration of solid fuel ducted ramjet SFDR technology, an air-breathing propulsion system that promised to extend the missile reach to 340 kilometers at high altitudes and 190 kilometers at lower altitudes. The SFDR program, launched in 2013 with initial consultancy from Russia, aimed to deliver this capability within 5 years. The first propulsion system test occurred on May 30, 2018, followed by another on February 8, 2019. By 2023, the Astra Mk-3 underwent flight testing, validating its SFDR propulsion, which included a nozzle-less booster, thrust modulation system, and sustainer engine. As of March 2025, two in-flight tests, FT-01 and FT-02, have successfully demonstrated separation mechanism building on prior ground tests and of the booster system. This milestone marks significant progress though the missile remains in development with air-to-air firing trial still pending. The path to realizing the Astra Mk-3 has been fraught with challenges, particularly in mastering the SFDR technology. Unlike traditional rocket motors, ramjet propulsion relies on sustained air intake to maintain thrust, requiring precise engineering to achieve stability and efficiency at supersonic speeds. Scaling this technology for a missile poses significant hurdles. The SFDR system nozzle-less booster and thrust modulation demanded innovative design solutions to ensure reliable performance across wide range of altitude and speed, Mach 0.8 to Mach 2.2 at launch and up to Mach 3.6 at impact. Early tests revealed difficulty in maintaining consistent thrust, delaying timeline beyond the initial 5-year target. While Russia provided early assistance, India's shift towards self-reliance means DRDO had to develop critical components like ramjet engine and ESA seeker without extensive foreign support. This transition, which while strategically vital, increased the complexity and time required for development. Integration of the Mk-3 with IAF platforms like Sukhoi Su-30 MKI and Hull Tejas required ensuring compatibility with existing avionics and launch systems. The missile, larger dimension 3.838 meters long, 178 to 200 diameter and weight compared to Mk-1, necessitated adjustment to aircraft pylons and flight dynamics. The transition from ground to air trials have been slower than anticipated. As of April 2025, while ground tests of the booster and separation mechanism succeeded, the lack of completed air-to-air trials initiated ongoing challenge in validating real-world performance against maneuvering targets. These obstacles reflect the broader difficulty of pioneering next-generation BVR missiles with cutting-edge propulsion, a task that even advanced nations have struggled to perfect. The Astra 3 development showcases a remarkable evolution in technology. Each development phase advancement shaping the final product. The shift from solid rocket motors mk-1 and mk-2 to SFDR technology in mk-3 dramatically extended its range and endurance. The ramjet ability to sustain thrust mid-flight allowed the missile to engage distant targets like AWACS, airborne warning and control system aircraft, strategic bombers, refuelers, enhancing the IAF's standoff capabilities. Building on mk-1 Russian designed radar seeker, later replaced with indigenous KU and X-band seeker, and mk-2's AESA radar, mk-3 integrates advanced electronics for precise target tracking. Its two-way data link enables coordination with launch platform and AWACS, improving accuracy against highly maneuverable targets. Early Astra design features cruciform wings replaced by cropped delta wings in mk-1 for better high flight control. The mk-3 retains aerodynamics lessons from its predecessor while adapting to the demands of ramjet propulsion, balancing speed, range and maneuverability up to 20 degrees of angle of attack. The impact of these innovations is profound, with a range rivaling or exceeding that of adversaries missiles like China's PL-15 or the US AIM-174. The Astra mk-3 positions India as a contender in global air combat. Technology. Its ability to engage targets at varying plus minus 10 km snap-down capability and speeds makes it versatile against a spectrum of threats from fighter jets to strategic assets. Moreover, its indigenous development reduces reliance on imports, aligning with India's Atmanirbhar Bharat initiative. The Astra mk-3, codenamed Gandiva, stands as a testament to India's advancing missile technology, blending sophisticated aerodynamics, cutting-edge internal systems, and advanced material to create beyond visual range BVR air-to-air missile capable of engaging targets up to 340 km away. Designed by Defense Research and Development Organization, the missile leverages lessons from its predecessors, Astra mk-1 and mk-2, while introducing groundbreaking features like solid ducted ramjet propulsion. Below, we dissect its aerodynamic profile, internal components, and role in advanced material in achieving its superior performance. The Astra mk-3 aerodynamic design is optimized for supersonic flight up to Mach 3.6 at impact and long-range engagement, balancing stability, maneuverability, minimal drag, while exact specifications remain classified. It design built on evolution seen in earlier Astra variants. Shape and dimension. The missile maneuvers approximately 3.838 meters in length and diameter 178-200 mm, making it slightly larger than mk-1, 3.8 meters 178 mm diameter. Its cylindrical body reduces frontal drag, creating critical for maintaining speed over extended range. Unlike mk-1's initial cruciform wings, which were replaced by cropped delta wing for better flight altitude, the mk-1 largely refines this configuration cropped delta wing, enhancing lift and maneuverability at high angle attack at 20 degrees. The missile features a pointed nose to minimize air resistance, paired with small rear fins or canard for precise control. These elements ensure stability across wide range of speed, Mach 0.8 to Mach 3.6, especially during transition from boost to sustained phases. The SFDR propulsion demands a design that supports air breathing efficiency. Air intakes, likely positioned along missile midsection, or are engineered to maximize airflow to the ramjet engine while maintaining structural integrity at supersonic speed. This adds complexity to intakes and must avoid disturbing missile aerodynamic profile. The Astra mk-3 internal architecture integrates three core systems: propulsion, guidance, and warhead, each pushing the boundary of missile technology. The mk-3 defining feature is air-breathing SFDR propulsion, a leap beyond the solid rocket motors of mk-1 and dual pulse motor of mk-2. The system comprises a solid fuel booster that accelerates the missile to supersonic speed Mach 2 post-launch, enabling ramjet ignition. Once ignited, the ramjet uses atmospheric oxygen to burn fuel, sustaining thrust over long distances. This extends the range to 340 km high altitudes, 15 to 20 km, and 190 km at lower altitude. A control system adjusts thrust mid-flight, optimizing for terminal maneuvers and at extended ranges. Unlike traditional rockets, the ramjet efficiency increases flight endurance, making the mk-3 ideal for engaging distance value targets like attacks or bombers. The mk-3 employs an indigenous active electronically SK-era radar ASR radar evolved from the mk-2 design to provide high-resolution target tracking, resistance to jamming, ability to lock onto low observable target. An inertial navigation system with mid-course updates ensure accuracy over long ranges. A two-way data link connects the missile to launch platform Su-30 mki or AWACS, enabling real-time course correction and target handoff. In its final approach, the Seeker fire and forget capability allows autonomous engagement with reported accuracy within meters even against maneuvering targets. The mk-3 carries a high explosive pre-fragmented warhead likely weighing 15-20 kg, similar to mk-1's 15 kg, designed to maximize lethality within 10 meters kill radius. A proximity or laser-based fuse possibility adaptive timing, ensuring detonation at optical distance from target, enhancing effectiveness against aircraft or drone. The Astra mk-3 performance hinges on advanced material that withstand extreme conditions while keeping the missile lightweight and durable. The Astra mk-3 guidance system is intellectually core of it beyond visual and air-to-air missile, enabling it to locate, track and destroy target 340 km away with precision. The Astra mk-3 employs an active electronically scanned array radar ASR radar seeker as the cornerstone of its guidance, making it significant evolution from semi-active radar homing of earlier missile designs and building on indigenous ASR seeker introduced in Astra mk-2. This ARS system operates in following stages. Post-launch, the missile relies on internal navigation system aided by mid-course update by two-way data link. This link connects the missile to launch platforms, fighter jet or AWACS, providing real-time target coordinates and trajectory adjustment. The INS, likely enhanced with GPS or India's IRNS Navic for precision, ensure the missile stays on course over extended range. As the missiles near its target within 20-30 km, the ASA seeker activates. Unlike passive or semi-active system that depends on external radar illumination, the ARS system emits its own radar pulses, actively scanning the target. The fire and forget capability frees the launch aircraft to disengage or engage over other threats, enhancing operational flexibility. The ASA seeker operates in Ku or X band frequency range 12 to 18 GHz or 8 to 12 GHz, offering high resolution for detecting a small, fast-moving target. Its electronically scanned beam eliminates mechanical gimbal limitation, providing rapid target acquisition and wide field of regard, likely 60 plus minus degree or more, crucial for engaging maneuvering targets. The ASA phase array design comprising numerous small transmit-receive modules allows for simultaneous multitasking and adaptability to dynamic combat scenarios. This sophistication ensures the Astra mk-3 can engage target threats ranging from fighter aircraft to high-value assets like AWACS or bombers.